I will finish to discuss a little bit about NES. So, first part of the talk will be divided in 4 parts. I will discuss 3 oscillations of 1 linear degree of freedom coupled to 1 NES. Then again, I will, by a similar but a little bit different technique, discuss the case of 2 degrees of freedom under initial impulse and how we can optimize or we can design the NES to obtain the desired result. I will discuss the case of 2 degrees of freedom system periodically forced. Then by analytical method I will show you how it works. Perhaps I will consider also the passive control of aeroelastic instability, but in a very, very academic and simple model of bridge. Okay, this is the first part of the talk. Let us go. So it is what I just said. All what I will discuss is, or almost is, based on a few references, but I will give a file where you could find these references. So let us go. So I will consider a 2 degree of freedom system, and what I will explain to you is based on this work by Oleg Gandelman. I consider 2 degrees of freedom, so I have main mass, so it is a unity here. So if you have lambda and k that are 0, you see that we have, and if in some sense if epsilon is 0, we have a very simple 1 degree of freedom without any damping. So epsilon is a positive small parameter, lambda and k are considered as constants, and I will analyze this 2 degree of freedom system by classical mean. I introduce V, that is the center of mass, and I introduce the relative displacement. So I can make a change in the variables to get this system, and from this system I can rescale by introducing, following Oleg work, a small parameter chi that is 1/3 of epsilon, and I rescale the system writing capital V, that is a small v divided by chi, capital W that is equal to W, and I consider I write again these equations in terms of capital V and capital W, but I keep only the main orders, let us say, of chi. So you obtain this system. Now I introduce the 1-to-1 resonance, as I did already. So I consider that the previous system is a perturbation of uncoupled linear oscillator with frequency 1. It means, okay, I consider here I have V double dot plus V, if I forget this, equals 0, and here W double dot plus W, okay, plus perturbation equals 0, so that I have exactly the 1-to-1 resonance. But to do this, again, I introduce delta parameter, but indeed this delta is 1/chi. So it's a little bit strange, but it will be valid if I can check that here in that term, that is the factor of delta, if this term is of order 1, it will be okay. Then to understand what happened, I introduce complex variable. So I will introduce complex variable in the sense of Leonid Manevich. So I introduce phi1 and phi2, and you see that in fact phi1 and phi2 are amplitudes and are there to measure the amplitude of the resonance, since here I introduce exponential IT here also to this is the consequence in my complex variable of the 1-to-1 resonance I introduce. So the complex variable, it is phi1 exponential IT is simply the velocity capital V plus I V, and I do the same for W. Okay, I introduce also conjugate variables, obviously, so you see that I could also write capital V, capital W, and the corresponding velocities versus phi 1, phi 2, and conjugate complex variables. If I write the system, if I write the equation, the system that is here, but using now the complex variable, I obtain the following thing. So I obtain the first equation versus phi 1, that could be written like that. So you see that I have phi 1 dot plus here I have this small parameter at order 2, and I obtain this equation for phi 2. So I have phi 2 dot plus perturbation, and you can see that okay, the nonlinear term occur in this second equation. Then I use multiple scale analysis, as it has been described by Professor Luongo. Here the small parameter is chi, so I introduce multiple times tau g by chi g t for 0, 1, and 2, and so on. And I introduce the by rule chain the derivative versus time in function of tau 0, tau 1, and tau 2 operators, and I look for the expansion of phi g like that. So for g equal 1 and 2, I have phi g 0 plus chi, phi g 1, and so on. At order 0, it is obvious from this equation, you see that I will get simply the derivative of phi g0 versus tau 0, that is 0, so it means phi g0 does not depend on tau 0, but on tau 1, tau 2 perhaps. At chi 1 order, I have this relation for phi 1, 0, phi 1, 1, and I have a more complicated relation for phi 2, 0, phi 2, 1. But these relations can be analyzed. So secular terms with respect to time scales tau 0 should be eliminated from previous equations. So okay, I consider versus tau 0 in both equations. I eliminated the secular terms, and I find finally okay, phi 1, 0 depends only on tau 2, phi 1, 1 depends on potentially tau 1, tau 2, and then I have this differential equation, but it is an equation for phi 2, 0 versus tau 1. Then, using Poincaré-Bennigsen theorem and criterion, Gendelman proved that phi 2, 0 evolves to an equilibrium. And okay, you can understand what happens if tau 1 is large enough, tends to infinity. In fact, you obtain here an equilibrium that is defined by this algebraic relation, and we can consider that we will be interested when tau 1 tends to infinity in the state reached by the phi 2 variable. So here I write phi 2, 0 tilde to say that, you know, the phi 2, 0 will not depend on tau 1. It does not depend on tau 0, on tau 1, but perhaps only on tau 2. Okay, by the way, the Bendixson criteria, okay, it says that the possible non-wandering sets of a vector field may be points, periodic points, and union of fixed points and trajectories. Here, periodic orbits are excluded because if we consider this equation, we consider real part of phi 2, 0, imaginary part of phi 2, 0, we obtain this this differential system, and if we consider the trace of a gradient, in fact, I have written, it is not clear because I have a problem in notation. Here it is imaginary part of phi 10, real part of phi 10. I define this as P of xy, and here this as Q of xy. If you calculate the trace of a gradient, you obtain that it is minus delta lambda, and so it is strictly negative. And according to Poincaré-Bennigsen, periodic orbits are excluded. Okay, it was a detail. Now I can do a similar treatment for the next order. So it is order chi2, and I can look at evolution of phi 1 variable, and it is governed by this equation. So if I look at secular term with respect to time scale tau 0 again, I have this relation. Then if again I consider in the limit tau 1 tends to infinity, the secular term with respect to tau 1 are absent if we have this that tends to 0. So in the limit tau 1 tends to plus infinity, the equation is simply given by, okay, you have here d phi 1, d tau 2, and here you have minus I2 phi 2 tilde 0 to the tilde here has been introduced in previous slide. It says that we take the limit versus tau 1 time. Okay, so now I can use this equation, so it's at this order, and I can use this equation. So here you see it is equilibrium state, and here and here it is evolution equation but versus tau 2. I can use these two equations. Then I can write phi 2 tilde, and phi 2 tilde corresponds to the amplitude, if we wait long enough in some sense, of the complex variable phi 2. By the way, if you look and if you remember, okay, you see that the phi 2, in some sense, if you take the modulus, it is associated to basic energy for the W variable. Here it is similar for the capital V variable, and if you go back to what it means, okay, we rescale, but mainly V is the amplitude of center of mass, and W is the amplitude of relative displacement. Okay, so we go to the calculation. So I introduce here polar form of this amplitude phi 2 tilde. I have the similar for conjugate. I introduce polar form for phi 1 amplitude and conjugate, and you see the real N2 and N1 measure the modulus of these two complex variables. I introduce the phase difference, and we obtain, in fact, two equations. These two equations correspond to first equation and the nonlinear relation between equilibrium state, and you obtain this equation that is, in fact, evolution equation of N1 and gamma 1 but versus tau 2 scale. If I combine these two relations, it is possible to write evolution of N1 square versus N2 square, and it is possible to eliminate N1 by using the previous algebraic relations, so that finally we have the derivative versus tau 2 of this quantity depending on N2 square, that is depends on another function of N2 square. So if we introduce capital Z equal N2 square, we obtain the following differential equation versus tau 2. And you see that in this equation I have lambda, that is the damping of the coupling between the two degrees of freedom. I have capital K, that is the nonlinear coefficient that has been taken here cubic, as you can see on the first slide. And this system is completely integrable But okay, integration introduces initial value of z, and by the way, it depends on initial conditions for x dot, y dot. That could then give initial conditions for small v, small w, v dot, vw, then capital V. So it is clear that we have a chain, and the initial condition for the system can be related to the capital Z initial conditions. And now, this relation that is completely integrable, you see clearly that we will obtain a function of z equal to 2. And the question is, what is the shape of this function? Okay, here I have taken a numerical example. Unfortunately, perhaps it is not a good idea, because I have taken critical parameters, and it is not so clear. Okay, I can, everybody seen that. Okay, in some sense, you see, the following thing occurs. If I plot here τ2, I have somewhere the following shape. Okay. If it is critical, you understand that perhaps we could obtain something. I try to plot. So it's not very, what I am plotting is not completely correct. It's simply to give you a shape, and if I have not a good situation for the parameters, I could have something simply. Sorry, that should be like that. Okay, so what does it mean? It means clearly that if you look at the function appearing in that system and leading to integrable system, you could distinguish these different shapes. And then what happened? The following thing happened, and I can explain the mechanism for energy pumping. If you choose initial condition, you start here. I have plotted zero, but in fact you have constants in integration of the previous system. And I recall that I have written that first you have to go to infinity in time. But in practice, you do not go to infinity, because epsilon is finite, and the infinity for τ1 is a large enough time, depending on scale of chi here, because I changed the small parameter. So if you take an initial condition, first you will reach the equilibrium, so you need to reach the equilibrium, then you follow the equilibrium, and here you have a bifurcation. And what is interesting? Obviously it is interesting to have this bifurcation, because you have a decreasing in amplitude of oscillations in the system, and to have a control it is what you need. But you understand that if you have a bad parameter, it means if you have not a critical situation, you will start from here, and here you will have a slow decreasing behavior that is governed, in fact, by simply the damping. So it is not efficient, it is linear damping. If you are with such a situation here, it could be interesting, but you have also, in some sense, to make the design of the bifurcation that is adapted to a given level of energy. If not, you wait a very long time before obtaining the bifurcation. So, and if you have a critical value that I have plotted here, you have a decreasing, because, okay, it's almost vertical. You have the critical situation with only two roots and not three, and it is similar if you start from initial conditions. So from initial energy not too far from the bifurcation, you have the explanation for the passive control. Okay, I have another comment with let us say Let us look at a situation that is perhaps not optimal. Something that is perhaps not optimal. That should be something like that. So I plot first. Okay. First I plot Z. Sorry. I plot here Z, and I plot tau2 after the curve. So you could understand the following thing, because Z is associated to initial, it is associated to what happens after waiting a time long enough, because Z is connected to, it is connected to N2, so it is the amplitude. Okay, Z is associated to N2, but it is connected by the equilibrium relation to N1. In fact, it should have been perhaps clever to consider N1, but here it is natural to consider N2. So what happened? If you wait a time long enough, initial condition for Z, in fact, are 0. But since you have a coupling between between X and Y, so V and W, capital V and W, if you wait a time long enough, you will have, after reaching the equilibrium, you will have initial condition for Z. So you have two solutions. Either your initial condition is somewhere here, after reaching the equilibrium, then you have this and you have a jump. But if you have an initial condition that is too small, in some sense, perhaps you will start from here, and here you will have this evolution that corresponds to a basic damped oscillation. So it explains that in the phenomenon you have a threshold of energy. If you do not are above the threshold, the energy pumping is not efficient. It is what we see in the first experiments I show you. I show you the basic system, 2 degrees of freedom with cubic coupling, but I said if the h, that is square root of 2h, it is initial energy in velocity. If it is not large enough, you see oscillations, and it was written on the figure, the pumping is not efficient. It is not efficient because the energy is not above the threshold. So, in some sense, the passive control, the nonlinear passive control is efficient if you have enough energy to control. If you have nothing to control, the system is able to deal with, to dissipate energy. Okay. But in the design, for transient, you have to take into account this phenomenon. It is what I have plotted here, because you see, bifurcations for Z occurs if real roots exist. Here I have plotted a case. I have plotted a case where you see it is not so clear. In some sense, I have plotted this part of the curve. So you have this, but it is even worse. I have plotted this part of the curve because I have no bifurcation. So what I have plotted here should be something like that. I have no bifurcation. And it is interesting to see that if you have also, in some sense, it could be analyzed that you have a critical value for the lambda parameter, and lambda parameter is associated with damping. So in some sense it's a damping, but you see, if you consider that it is specific damping, it means with a frequency that is 1, it is 30, it is very, very high specific damping, so it never occurs in physical systems. Okay, but you have a limitation, a critical value for the damping. Okay. I will not give details, but we use the same techniques in this paper, and it has been applied to study the occurrence of pumping, but in a system where you have 2 degrees of freedom plus oneness. And it is possible to introduce then 2 time scales, epsilon 1 and epsilon 2, depending on the 2 masses you consider. So in each case we consider that the auxiliary masses of an S is small versus M1 and versus M2. But you could have two scales. And we studied in this paper now the competition between the two modes coupled to the nest, according to initial energies split into the modes. It means that now you have two masses, you have two time scales, and in some sense you have two such bifurcation curves that could be in competition. And you could have, for example, you could have first a control, because of a coupling, you could have a control of a phenomenon, then a control of another one that occurs according to the different time scales. So this competition between the two time scales and the two, the effect of the nest and the two masses has been studied in this paper. Okay. Now let us come back to the same kind of problem. It means 2 degrees of freedom, and in some sense let us try to use another technique to make optimization of a nest. So it's based on a paper with Leonid Madevich and Emmanuel Gourdon. So we consider again a 2 degree of freedom system. You have a main mass here. So it is damped in that case, and you have these two terms that corresponds to coupling to the nest. So it is small mass M, that is small mass, and you have a damping, and you have a cubic coupling here. So again, I consider initial condition. For example, only initial condition in velocity for x1, that is the mass we intend to control. Again, we introduce here two new variables. Okay, u tilde is simply x1, but here we introduce the relative displacement. Then we introduce capital U1, capital U2 by rescaling the variables versus initial energy. Okay, we introduce the frequency K1 divided by M1. We introduce the small parameter epsilon, that is the ratio of mass. We change time using this eigenfrequency omega, and we introduce small parameters or parameters by using this change of variable. Then we rescale the displacement, and finally we obtain these differential systems with U1 that is associated with the displacement of the main mass but rescaled, and U2 that is associated with the relative displacement of the two masses that are coupled. Okay, here you see that we wrote the system like that. Why? Because okay, if epsilon is 0, you see that here you have frequency that is 1, and here we introduce U2 to prepare the 1-to-1 resonance. But here it is U2 minus U2, since it is clear that in the second equation I have a purely cubic nonlinear elastic term, and I have no classical frequency, so this is why I introduced here. Okay, so it is what I said. We consider that oscillations occur near resonance frequency omega, so it is near 1 for the time tau we introduced. And we did as previously, but you know the scales are we played with scales in a slightly different manner. So you see, I consider the same equations, but here I have a bracket term, and again I do something that could appear as a little bit strange. I introduce delta equal 1 over epsilon, you see, so it is clear that, and then I will forget, I will say, okay, delta will be a parameter. So writing and thinking to this coupled system in that sense, it means here it is a perturbation of order 1 in epsilon, if I forget that delta is 1 over epsilon. But it is similar to what I said. To have something that will be correct, it will have to be verified that this term, the delta is of order epsilon 0. If not, it will not be correct. Then again, I introduce Manevich complexification. So phi k is epsilon minus I tau, because I use the rescale time. Again, it is velocity plus displacement, similar the conjugate terms for k equal 1 and 2. And I consider multiple scale analysis by introduce multiple times tau 0, tau 1, tau 2, and by expanding phi k versus epsilon. So it looks like what I did previously. So again, we obtain this differential equations versus tau 1, and okay, I have also complex conjugate ones, but it's not necessary to write. And if I multiply these equations by phi 1 0 star and phi 2 0 star respectively, it is possible to combine to obtain this evolution equation, but for modulus of phi 2 0 square, modulus of phi 1 0 square, and here you have the same kind of function, and it is evolution equation versus time scale tau 1. Okay, if there is no damping, I have this conservation of energy, so this term is a constant versus tau 1. If there is damping, we can consider that this equation 3 is a differential equation with respect to phi 2 0 square, written with the right hand side. Okay, and then if we introduce Laplace transform, so capital psi is Laplace transform of this, G is Laplace transform of that terms, we are able to write capital psi of S is equal to this function. Then, okay, if I write inverse Laplace transform, I get this. But it's not so easy to deal with that, so we could consider approximation of a solution, and we can take expansion, Taylor expansion of this integral in series in the vicinity of tau 1 equals 0. Then I obtain this expansion, I truncated here, where h0, phi 1, 0 are known from initial conditions. And the derivative and all higher order derivatives can be found also from initial conditions and initial equations of motion. Okay, so I do simply the following comments. I do not show you a lot of results. When energy pumping occurs, the approximation up to order 5 of this H versus tau 1 is enough. It is sufficient. And then from this analytical expression, I can use this analytical expression to choose or to determine the parameters or the influence of each parameters on efficiency of energy pumping. And if I consider that parameters of linear primary structure are given, because sometimes the primary structure is an existing one, I can study the influence of eta or C parameter, and you see that it is these two parameters could be related to the coefficient of the cubic term, the damping of the coupling. Okay. And in that case, we did so this analytical work and numerical works, but Emmanuel Gourdon checked that the prediction of the, let us say, efficient energy pumping have been verified experimentally from measured data. Okay, now I will discuss, but you see, I will repeat almost all the time the same technique. So I will consider now 2 degrees of freedom, but I consider that I have a harmonic forcing, and I consider it is similar to what I did before. So I have a main mass. So if eta tilde K3 are 0, I have 1 degree of freedom with external periodic forcing that is given here. But now I introduce a coupling between the two masses. Here it is a coupling for damping, and here it is coupling for elastic nonlinear part, and I assume that I am able to build a cubic nonlinear part. Okay, with initial conditions. With initial conditions, we will see. Then we introduce again new parameters. The main one is the ratio of mass, that is considered to be small. I introduced omega 1, that is eigenfrequency of first oscillator, and I introduce some parameters, mu1, depending on mu1 tilde, simply to say that it will be small parameter, it is damping, it is classical. I have the same thing for the damping between the nest and the main mass, and I assume also that the nonlinear cubic term is small. I introduce a perturbation analysis. Then I introduce here a new external frequency rescaled by omega 1 eigenfrequency, and I obtain the following system. So I obtain this system now, and if I introduce, it is similar, I introduce coordinate V1 of center of mass, V2 is the relative displacement, so I can write reverse equations. If we neglect in these equations terms epsilons 2 and higher ones, I can write the following equations. So here you have a linear part plus perturbation with eigenfrequency that is 1. Here you have this, let us say, order 0 part plus perturbation equation, and we will analyze. So we will analyze again the dynamics of this coupled system when the main resonance occurs. So we will assume that capital omega is close to 1, and we will write omega is 1 plus sigma epsilon. Again, I introduce complex variables, but since it is clear, it is as usual, since you have external forcing at frequency capital omega, I introduce phi k, phi k exponential I omega tau is equal to dvk, velocity of vk plus I vk. So it means phi k in some sense is the amplitude of the complex variable I built here, but it is in some sense the amplitude of the oscillation of the system forced by f sine capital omega tau. Okay? And then, as usual, I use the multiple scale method. So it is possible to write, as we said, the Vk and the displacement and velocities versus the complex variables. And using the multiple scales, for the first equation, we obtain the following thing. So I obtain, I started to write what happened with epsilon 0, epsilon 1 terms. So you have this equation, but we can get rid of epsilon or terms of orders of epsilon greater than 2 because we introduced the omega equal 1 plus sigma epsilon. So this term will be simply minus I divided 2 by epsilon, and you see that it could be useful to finish the multiple scale analysis. So for the first order equations up to epsilon order, we obtain epsilon I omega tau 0 multiplied by, here you have epsilon 0 order, it is simply d phi 1 d tau 0 plus epsilon term, that is this one, plus epsilon minus I omega, it is conjugate terms, and plus higher harmonics. For the second equation, we can do exactly the same thing. So we can write what happens up to epsilon order. So we have this, and here I kept this term. So the equation can be written like that, plus conjugate terms, plus again higher harmonics of omega tau 0. And neglecting the epsilon 1 order, I obtain this relation plus conjugate plus higher harmonics of tau 0. And now what can we do? Now we can take advantage of what we have written. So at epsilon 0 order for first and second equation we have the following dynamical systems. The first relation means that phi 1 does not depend on tau 0 but on tau 1, tau 2 perhaps. And the second equation we have to say something. You will see. Then I will process. I have written here averaging, but it is not correct. It is not averaging. I will consider that I write I am looking at the evolution of the dynamical system, but around the main amplitude. It is the sense of phi 1 and phi 2. They are complex amplitudes around the main harmonic term. So for phi 1, it is very easy. Phi 1 does not depend on tau 0, so I can consider it is clearly a constant of tau 0. Versus tau 0, it is a constant. By the way, here it is a mistake, it is the phi 2. But in this relation, phi 2, it is not clear. Even if phi 1 does not depend on tau 0, but only on tau 1, it is not possible to claim that phi 2 will not depend on tau 0. Then we consider the following thing. We consider that if we wait a long time enough, the dynamics of the system will be captured by an equilibrium. So when tau 0 tends to infinity, or at least in practice for time long enough, phi 2 will reach a steady state with d phi 2 d tau 0 is 0, and I have this relation between the amplitude of phi 1 and amplitude of, between the phi 1 and phi 2 variables, sorry, that are complex amplitudes. Now, again, I have, initially I have a dynamical systems which has dimension 4, and then I will show you that we are able to reduce what happens to a two-dimensional system. I introduce now the polar form of phi 1 and phi 2 as in the previous case, but from the previous relation 3, I recall this one, it is clear that in the polar form we could obtain a relation between n1, that is the modulus of phi 1, and n2, that is the modulus of phi 2. Well, that is given in that form. In this relation you see that we have the damping parameter and we have the stiffness of a nonlinear of a cubic term. Okay? And also it is possible to write delta 1, the phase here, versus delta 2 and n2. Okay? This relation defines what we call often the tau 0 invariant. And if we consider now what happens at order epsilon, I have two equations at order epsilon, one for phi 1 and one for phi 2. But by the way, it is better to consider the first equation. Why? Because it appears clearly here. You see, this equation here I start at epsilon 0 order, here at epsilon 1. So in fact, it is better now to consider. Yes, now it is better to consider phi 1 at epsilon 1 order, because in fact phi 2, if I go back to what the variables means, the second equation should be at epsilon 2 order in fact. So I consider simply the first equation that I can obtain by multiple scales, that is this equation, and then I will consider evolution of phi 1 versus tau 1. And you see that this relation depends on phi 1 and phi 2 and also on the amplitude of the forcing. But if I consider that I am studying now the evolution of this system but around the tau 0 invariant, I can replace in this expression phi 1 by by the function of phi 2 that I obtained from relation 3, so that from this relation. Okay? If I do this, I can write again the previous system in the following form. I will have the evolution of n1 versus τ1 plus the evolution of the phase versus τ1 plus some complicated perhaps functions fr and fi. It is not so complicated. These are these equations, but in these equations I should replace phi1 by the values that I obtain in the τ0 invariant. So finally I am able to write that in the polar form n2 versus τ1 depends, the evolution of n2 versus τ1 depends on simply a function f1 of n2 delta 2 divided by here denominator, that is g of n2, and for delta 2 it is similar. I have a function f2 and I have this special form for denominator with the same function g. And now it is perhaps enough to study classically for the next step the fixed points and singular points of previous systems. So classical fixed points corresponds to f1, f2 equals 0, but g is not 0, and h1 I recall, h1 it is this one. So you see, when you see the form, it is not 0. So in fact, it is enough to look at f1 equal f2 equals 0. It gives the classical fixed points corresponding to periodic solutions. And in fact, it is enough to look for singular points that corresponds to false singularities. Why? Because it corresponds to these three equations that are 0, but g equals 0 in fact gives you the value of the maximum here. You obtain the n2 corresponding to extrema of the τ0 invariant. Okay, so to solve the three equations, in fact, is not so complicated because we can select values for n2. So here I have plotted the general shape of a τ0 invariant. So I have plotted n1 versus n2 for these given parameters. And what is interesting? Something is interesting. It is if you choose to explain that you see in that form you see again in some sense the z. So you can understand that if we choose perhaps badly the parameters of coupling, here I could also obtain a curve without multiple states. If you take here n1 is a constant, you could have several solutions n2. But it is due to the fact that I have chosen these values of parameters that gives multiple states. If you take a bad design, you have here a monotone branch, perhaps not linear but monotone, and you have one n1, one n2. So we will not have the pumping phenomenon that I will explain. So why can we use the previous situation for passive control? In fact, we have three cases. Because here you have a first branch from 0 to here. Then you have a second branch from here to here. If you make stability analysis, this is unstable. Here you have a third branch. And now I will try to look for classical fixed points. And we will have three situations. Either I will find, for example, classical fixed points here at low level of n1. n1 is the polar, in the polar form, it is in fact associated to the, let us say, amplitude of oscillations of the main mass. So if you have a fixed point here, it means for application, it is periodic solution, it is oscillations of low amplitude. Okay, it could be something that can be perhaps not too bad for the main structure. The second case is you could have fixed points on that branch here, but it means perhaps at with I value of n1. In that case, it means if you have external amplitude of forcing giving such a fixed point, perhaps it's not a good design for the nest because you will have a periodic solution of high amplitude. And you have a third situation. The third situation will be the following one. In fact, the dynamics, and I will show you soon, the dynamics of the system, and it is the case 3. For medium amplitudes of forcing, there is no fixed points. It means you have no fixed points here, no periodic solution of high amplitude, no periodic solution of small amplitude, but you have something else. And the something else is a kind of cycling around the tau zero invariant, and I will describe qualitatively what happens. You take initial condition, I will show you curves after. You start from, let us say, a point here. You wait, you reach the tau zero invariant, and you have evolution. You arrive at that point, then you have a jump, you have a bifurcation. Then perhaps if you have enough energy, again the behavior will increase. You reach this point, you have a jump. And so you have a kind of cycling here. You have exchange of energy, and this exchange of energy is quasi-periodic. Non-periodic. Okay. So this case 3 is interesting because in fact it is if the system is well designed, it is a way to have with this quasi-periodic, with this cycle corresponding to this quasi-periodic, non-periodic behavior, it is a way to limit the amplitude of vibrations of the main mass. It means we limit the amplitude of vibration of N1 because in some sense, after, what I explained to you is after a transient, you have evolution, but after the evolution of the system is trapped, and in some sense it is trapped at a maximum value for N1 that is here, and it means it can define also the maximum value of vibration. You can say the system can accept without be destroyed, and it is a way to make a design of an S efficient for a given maximum value, let us say, of external forcing. Okay, so it is what I explained here. If you say, okay, for some interval of external forcing, I want to design the nest. So for all these values, you could solve the previous equations to avoid to obtain either case 1 or case 3. But what does it mean? Case 1, it is, okay, periodic solutions but of low amplitude. Case 3, it is quasi-periodic but at limited amplitude after a transient that could be chosen as short as possible, but never case 2, because case 2 corresponds to periodic solutions of large amplitudes. Okay? And if you process like that, you could make a design to control the forcing effect. I have to tell that, okay, why? There is a limit. I said it is to control the effect of a periodic forcing. But if you have initial conditions providing a high energy in the system, obviously you will have a transient, and the nest will be designed to control the forcing effects. So the transient, the nest could be not efficient, so you could have perhaps a long transient at high amplitude of oscillation before seeing the efficiency of the nest. So in some sense, to make something efficient in practice, you have to know what is the level of initial energy due to initial conditions, and what is the maximum level of periodic forcing you have to consider. Okay. It is a kind of cooking to make to design nest. Okay. Then I will tell you a few words about that case. So it is a very simple model of bridge. So it means we consider, we consider the deck of a bridge, and you could have the banding effect and rotation, but it's very academic because we consider, in fact, if lambda epsilon, k epsilon are 0, and if you suppress these equations, you see that you have a coupling between phi, that is the bending, and theta, that is the rotation angle. And here I introduce only the linear part. Okay, it is a classical example from the book of Blewins about aeroelastic effects. Okay, so, sorry, I consider these equations. So you have 2 degrees of freedom for the bridge, and we couple an S. The S is given by these equations, and again you have damping and coupling by the cubic part. So it is always the same thing. Here I rescale the model. So you have 3 second order differential equations. You have phi, theta, and here the interesting thing is this capital psi. It is the S hidden here. So you have here you have a new parameters with some spatial orders that are governed, you know, both by the multiple scales method I will use later and the values of physical values of parameters. Okay. So what I am explaining briefly here is based on a paper with Bastien Vorigo and Leonid Manevich that has been published in Journal of Sound Vibration. In fact, the previous system, you know, these 3 equations, we could substitute values of acceleration and integrate some equations so that we can reduce the previous system to a single degree of freedom system. In fact, you have psi double dot, so here you have a nonlinear part, equal to epsilon, it's a perturbation, you have f of t plus k epsilon I. F of t has the following form, q1 and q2 are complicated coefficients, and I of t is this integral, okay, it depends on psi 3, so it's not exactly 1 degree of freedom, but it's integral differential equation depending only on psi. Okay? Here I did, as usual, I introduce mu coefficient. It's not correct, but it means I forgot at once. In fact, here I have 1, but I write epsilon mu. So here I have now a perturbation term, but I will have to check if I am honest that mu multiplied by this bracket is of order 1, as I already explained. Then again, we can introduce the complexification. So we have phi that is, we do not see very well, but in fact I have phi versus psi star. I can obtain the reverse expression, and then I can write the singled off versus the complex variable phi. So I obtain this plus these terms, and these terms are coming from the integral terms. Then again I make multiple scale analysis. I have epsilon that is a small parameter. I introduce multiple times. I expand the complex variable versus time scales, and finally we can write successive orders. So at epsilon 0 you have this equation. That means I am able to write this solution. At epsilon 1 order the equation can be written in that way. Now I have to suppress the secular terms, and I obtain this equation. In this equation again I have q1, q2, and I have written that it depends on different coefficients and initial conditions, and I have this term c epsilon of t that is an integral term, and it is this equation. You see that it depends on phi 1, 0, it depends on the multiple scale analysis. And c epsilon could be, the expression could be improved by introducing this function, and finally the c epsilon to 0 depends on h function that is complicated, and you see that epsilon has this form, and it is interesting, it starts at epsilon order, but you see that you have also epsilon here in the integral term. So it is quite technical, but we can distinguish now 3 cases. We can distinguish first cases when omega is close to omega 1, a case when omega is close to omega 2. So omega 1 and omega 2 are the frequency of the 2 degrees of freedom initially, and the case where you have a resonance, a global resonance of in the differential systems. Okay. If we consider these different cases, we have different differential systems, but they all have the same kind of form. Okay. In the first case, the omega 2 does not generate resonance term. It is related to what Professor Longo explained. You have a non-resonant case. In that case, in the second case, we consider we have omega close to omega 2, but omega 1 does not generate resonant terms. And here on the third case, that is the most complicated one, we have in fact a resonance, and we could introduce omega 1 is close to capital omega, omega 2 is close to capital omega, and we introduce a capital omega that is close to all the frequency. So we have technical cases. If omega equal omega 2, we choose omega, capital omega is omega 1. Otherwise, we take the middle of omega 1 plus omega 2, but it means it is simply a technical way to say that I have this approximation. Then, in that case, the external forcing is could be expressed like that. I have the external forcing that is I have main order plus here it is tau 2 scale, and finally I could write that this term is written versus it is this form that is resonant plus non-resonant term. Okay, if I introduce some constants, you see here I introduce Q2 and I introduce a polar form Q2 and phi depending on the quantities of in the system. Finally, I can show that the dynamics of the initially 6-dimensional system is governed by this, in fact, 2-dimensional differential equations, but at time scale tau 1. Okay, then it can be studied, and if we wrote in fact the three resonant cases I talked about, in every case I have the same kind of differential system. It means if I use a polar form for phi 10 with amplitude real A and phase gamma, the differential system is governed by these coupled two differential equations versus tau 1. And in all the cases, we have the same kind of expression, except that, okay, if I said that 1, 2 and 1, 2 represents the three cases, omega close to omega 1, omega close to omega 2, and the global resonance case, I have slightly different constants in the general form of the differential equations. Okay, so here are given these equations, delta 1, delta 2, but the form is quite similar. Okay, and I have also, I can write the system in that form with different values for S1 according to the resonant case. Now it is interesting because we could study stationary points of the phase portrait that corresponds to periodic vibrations. That they are governed by these equations, and this equation is a cubic equation in the variable that is square of amplitude, and we can rewrite this equation in that form. So analytically it could be studied, and we could also study versus parameter what happens, and it is easy to consider the conservative case to say we suppress the damping, so lambda equals 0 in the equation, and then the study could be the summary of what we are looking for is given by these equations 9 we solve in capital delta and A. Okay, so now it could be discussed. We could discuss versus parameters of the equations. So for delta between minus pi and pi, we have this condition for stationary vibrations, and we could make the analysis versus the discriminant of the equation that is written here. So if r is negative, we have 3 real roots. If it is positive, we have only 1 root, and we can analyze what happens. We have saddle points and quasi-linear center, and only a center in the other case. Okay. Now the differential equations depends on the Hamiltonian system H that is written here. And we could consider the, Manevich said limiting phase trajectories. It corresponds to a separatrix H equals 0, and it gives delta equals 0 or pi, and here you have the equation for A, that is 0 or this cubic equation. So again, we could make a discussion, and we observe that we have a transformation of the phase plane versus the critical value of parameter alpha that is given here. So again, the limiting phase trajectory, we could say that if alpha is smaller than the critical value, the H equals 0 curve encircles the non-resonance quasi-linear center. If we have alpha greater than alpha critical value, it is no longer true, but the curve H equals 0 encircles the resonance center at delta equals 0. If alpha is greater than 2 alpha 7, you have this situation, and nothing occurs for greater value of alpha after 2 alpha critics. So we could plot such figures. It is not very clear, but here it corresponds to alpha equal alpha c. So you see in black here, you have a limiting phase trajectory that is here, and the critical point is there. Here the value, it is a little bit more complicated. You have this, the curve is like that, and it encircles this point. In fact, here it is the amplitude. Here it is the phase, it is delta, here it is the amplitude. So when delta is 0, you have the center at 0, and the separatrix is around this center. And it is similar description for the other cases. Here it corresponds to alpha greater to alpha 2 alpha critical. You have nothing new. But the study of these limiting phase trajectories and the dynamics of the Hamiltonian can be used to predict the asymptotic behavior of a system, because it depends on parameter capital F. And something is interesting, in fact, it is the physical meaning of a parameter. It depends on initial condition, but it depends also for the bridge on wind velocity. In fact, it depends also on self-induced oscillations. So alpha F2 in fact is not fully constant. Alpha is a constant, but it has a small evolution. And we could use this qualitatively and the Hamiltonian dynamics to make the design of an S. And it is what we did here. It is an academic example, but we have taken the value of capital K that is associated to the coupling, and you have here 2 curves. In fact, we plot the displacement of phi and of theta, that are the 2 parameters of the 2 modes of the bridge I consider. In the red case, it is what happens in the quite resonance and stable case without NES. In blue, you have what happens with the NES. And you see that the amplitudes are very small, because in fact here you see that I plotted the dotted line, but in fact the amplitude of the bridge are diverging, are very high amplitude, and we see nothing if I do not curve the curves. So it means by this study of dynamical reduced Hamiltonian we can make a design. It is qualitative, but it is perhaps not optimal, but you see that it works. It could be used to make the design of an efficient passive control. Here, this is an example. You can see also what happens. In the first case here, we have chosen the coupling. It is too low. So it means the K is too low. So we have to wait before the displacement grows up to a critical value, then the beating associated to the behavior of the Hamiltonian system starts. So it means then you have a beating and you have a control. But the problem is we have to wait a quite long time, and we have first to have large enough oscillations before the beating is starting. Here it is the contrary. It is the K is too strong. So first we have perhaps an efficient, transient, then the beating is starting, so we have a control, but in some sense here perhaps we wait a long time, and it is another case of control, but if you say that the control could be associated to this exchange of energy due to the Hamiltonian, it is better to choose the well-balanced value, and you have at once the exchange of energy is starting, and you have at once a limited value for amplitudes of the two degrees of freedom, since here again in blue and in red you have the amplitude of oscillations of phi and theta. Okay, so I stop for the first part, and I will finish with some other considerations. So, okay. Now I will go back to some academic models, but with, you will see, perhaps non-smooth terms, so it could be potentially interesting, but also some, in some sense, some internal variables, even if they are not perhaps written directly in the non-smooth form I explained in the first part of my talk. So we will consider academic model. Case 1, it will be Book-Venn but Dahl model plus a non-smoothness. So I will give some numerical example. In the second case, I will consider another value of a parameter that defines the Book-Venn model. I will consider then a cubicness, and I will make a few comments about gravity effect, you will see. So let us go to what I call non-smooth systems. So, okay, the first example I already described is I take one main degree of freedom with mass 1. It is academic, a coupledness with mass epsilon directly, and here the nonlinear coupling is not smooth but piecewise. Okay, so y1 is displacement of main system, y2 of an S. And without ness, by the way, you have this classical 1 degree of freedom oscillator. So at the resonance, the amplitude is more or less F0 divided by 2 psi, where psi is not 0 and is the specific reduced damping. Okay, now the second case I will consider, and it is that case I have distinguished several cases. It is a Book-Venn model coupled to an S. So Book-Venn model, it is first equation and third equation, and Z in some sense is a kind of internal variable. And you see that the Book-Venn model depends on A, beta, gamma, and the exponent n. Okay. So this is why I said n equal 1, n equal 2, okay. And here I have an S with nonlinear part, and this nonlinear part, you have this property. This nonlinear part could be smooth, cubic, or non-smooth, piecewise linear, for example. Okay, and we considered, but I will not discuss, but we considered also this kind of things. It means the main mass, but here you have U is internal variable, and as I described, you have this differential inclusion, and you couple this to an S. Okay, we discuss also the possibility of designing an S with purely nonlinear function. Okay. So I come back to what I said before. So now I will look DAL model for n equal 1, gamma equals 0. Let us start. By the way, in the DAL model, what happens? If I plot eta versus y1, but you see that if you remember, it is difficult, but if you remember what I have plotted, it is, yes, it is that case. Eta, it is simply everything except external forcing and inertial term. Eta, it is everything here. Okay, so if I plot this, you have some hysteretic behavior. Okay, so it is internal variable, another way to design hysteretic behavior by the Bookven, so-called Bookven model. And here you have phase portrait. Okay. Now, as usual, I make the change of coordinates. So center of mass, relative displacement. So the three equations are now governed in new variables W, V, W, and I keep Z in that form. Okay, so as usual, I introduce complex variable of Manevich. So phi 1 is for V, phi 2 is for W, and phi 3 is for Z. So here you have the expressions of V, W, Z versus phi 1, phi 2, and conjugate, and so on. It is as usual. By the way, if you introduce this relation, for example, let us say for W, the acceleration could be expressed in that form. It means only versus first derivative for phi 2 and, okay, phi 2 star, and the exponential I omega capital T is the time I introduced in my system. Now I am interested, you see, from previous equations, for example, for differential equation associated to W, I will obtain phi 2 dot equal exponential minus omega capital T by a function depending on phi 2 star, phi 1 star, phi 3 star. Okay. And we will study what happened close to the one-to-one resonance. So again, I will introduce multiple time scales, tau 0, tau 1, and so on, versus time capital T and small parameter epsilon. And I will take projection on first Fourier coefficient. It means I will try to make the calculation of that function, but either I will able to prove that the phi 1, phi 2, or phi 3 does not depend on tau 0, but perhaps on tau 1, tau 2, and so on. Or I will assume that after time tau 0 large enough, I will reach asymptotic state, so I can consider that the reach phi 2, phi 1, or phi 3 does not depend then on tau 0. And again, I will study modulations of the dynamics around the asymptotic state, as I explained. Okay, so I introduce here a function, but it is due to the piecewise linear, nonlinear function I introduced at the beginning. It is the result of a calculation of this function, again, assuming that phi 2 and phi 2 star do not depend on, in some sense, on capital T, perhaps after reaching a steady state. Okay. Now, if we use the complex variable of Manevich, and I have written average system is not correct, the projection on first Fourier coefficient, phi 1 is associated to V, so I obtain the following equation. In fact, it is linear. You can see you have dependence of you have phi 1, phi 2, phi 3, but it's linear. Phi 2 is associated to W, and you see that you have the influence of a non-linear term. I obtain this equation. And something is new and interesting. The third variable, it is Z. It is associated to phi 3. But as perhaps you noticed, the differential equation for Z is of first order. So if I make a projection on Fourier coefficient, I do no longer obtain a differential equation, but I obtain an algebraic equation. It is simply a kind of manifold, and I have now an algebraic relation between phi3 and phi1, phi2, and the conjugate terms. In fact, very soon I will introduce a polar expression of phi1, phi2, phi3. This equation will give potentially a relation between n3 delta 3, the polar form of phi3, and the polar variable associated to polar forms of phi1, phi2, and conjugates. Okay. But let us first consider multiple scale analysis. So at fast time scale, so for tau 0 equal capital T, then slow time scale, I process. I assume also, okay, it's for analytical reasons. In practice, you could go to 1 minus A over A equal 1. It works, even if I have written epsilon A0, but it's as usual in some multiple scales method. Okay, let us forget. I assume that this parameter is of order epsilon. Then, if you look what happens in the dynamics, you have for phi1, again, phi1 does not depend on tau 0, it is a constant. So, for the average system, it is correct to assume that phi1 does not depend on tau 0. It is not true for phi2. For phi2, I obtain this evolution that will define again the tau 0 invariant. It means I will assume that phi2 first reach a steady state for tau 0 large enough, and at epsilon 0 order, I obtain this algebraic relation between phi3 and the other variables. But you see, it is interesting, here I have phi3 depending on, okay, here I have also phi3 star, but in fact I have a relation between phi3 and mainly phi1. So it is what I explained. If phi2 reach a steady state when tau 0 tends to infinity, I can consider that I have a tau 0 invariant given by this relation. Again, in polar form, I can introduce phi1 equal n1 exponential I delta 1, and if capital phi is the state reached by phi2, I introduce this polar form. Again, I have the same invariant manifold than in the same thing, except that perhaps G is now not given by cubic but by piecewise linear function. But it is quite similar. Okay, again, I can make a stability analysis to guess stability borders. So I will obtain a result. And I can make also analysis of what happened for the epsilon 0 order of the hysteretic term. It means the third equation. So if I write everything in polar form, in fact I have complicated the expression, but it is possible to express n3 cosine delta 3 and n3 sine delta 3 versus functions that depends only on n1 and delta 1. This is the only important thing you have to notice in these complicated relations. Then again I plotted the n1 versus n2 tau 0 invariant, so you have the same shape than previously with stable, unstable, and stable branch. Okay. And now we can also study what happened at epsilon order, but around the state that has been reached when tau 0 tends to infinity, the state reached by phi2. So I consider the first equation versus tau 1. So this is this equation. And in this equation, I could replace phi1 by its expression versus capital phi. It means phi2, but at tau 0 infinite. And you see that here I have still phi3. But it is possible to introduce, so in this system, in the same way I already did, I introduce the polar form of capital phi, n2 exponential I delta 2, and it is possible to reduce the dynamics of the 5-dimensional differential system, the initial systems, to 2 differential equations. And here you have this relation with n2 depends on n2 delta 2. It is similar for delta 2, except that you have here, you see in psi and sigma, you have the n3 and you have here functions of, okay, it is a little bit complicated, but it could be expressed in n3 sine delta 3, n3 cosine delta 3. So finally, it is possible to say that I obtain analytically a reduced form, and it is simply n2 and delta 2 are governed. Probably, yes, it is the details are written here, so it is what I am explaining. Finally, it is possible to prove and to write analytical expressions here that n2 and delta 2 depends again on reduced dynamical system with f1, f2 and g1, g2. You have here the expression, and again it is possible to so it's not very important to look at the expression, except to see that I could have explicit expression of the function of n2 delta 2 governing the differential evolution of n2 and delta 2 versus tau1 scale. Okay, so I have again this system, and again I can study ordinary fixed points or fault singularities, but fault singularities corresponds to G that depends only of n2 equals 0, so we obtain very easily n2 values. Then it is enough to look for delta 2 values, and there is a small miracle in the two equations. Okay. I'll show you a few numerical results because it is enough to, in some sense, after all, it is enough to consider such picture. So what happened? I have chosen some given parameters for the initial system. G1 equals 0 is given by yellow curves. It means for two values of n2, I have G1 equals 0. It corresponds to two extremal point, the maximum and minimum points in the tau0 invariant. G2 equals 0 is this curve. It corresponds in fact to the absolute value that is in the DAL model. And I have f1 of n2 delta 2 equals 0 in blue and f2 in green. So what happens? For example, you have intersection. You have here intersection of green and blue. This is a classical fixed point. But you have here intersection of yellow, blue and green curve. It corresponds to fault singularity. Here also, and here also. And what happened? Okay, it is possible, it is difficult, but with this picture we could make zoom. It is possible then to look at phase portrait to see what happened around the either fixed point or around the fault singularity. Here you have fault singularity, you have a saddle node, dynamics is typical. Here you have, I remember, a fixed point, and it seems to be a stable periodic solution. Okay. If we change slightly the I do not know if I change here. Do not remember. No, it is the same. It is always 37 for F0. Okay. So simply it is I examine in detail what happens around 5. So you see around 5 you have here a center, you have a periodic solution because the fixed point will be stable. But here I make a zoom around 3, and here it is a saddle node. Okay? So we could study what happened. Then, why is it important for the dynamics? I will try with these three pictures to explain what I already explained previously. You start here from initial condition. So you have in red the tau0 invariant. Here you have initial condition, and I make numerical integration of the full system, initial system. From initial condition for the initial system, I compute initial conditions for N1 and N2. So I start from this point. Then, after a transient, I reach the tau0 invariant. But I have modulation around the tau0 invariant. Then you reach that point. In fact, it is associated to fault singularities. Then you have a bifurcation, you have a jump. Since you have energy large enough because it is due to F0, you have again evolution around tau0. You arrive here, it is again associated to another fault singularity. Then you have a jump. And it is not at all obvious only from this picture. But if you plot N2 and N1 versus time, you see that after a transient, that is not perhaps so long, here it is multiplied by 10 power 3 or 4, I don't remember, so it is long but not so long. You have a kind of beating phenomenon, but it is clear. The beating phenomenon here, you have a kind of you have a jump, then you have evolution, then a jump, evolution, then a jump. It is associated to the modulation around the stable branch, jump, modulation around the stable, jump, and so on. And it could be a quasi-periodic behavior, and it could trap the behavior of the system in this kind of that appears in the tau-zero invariant. Okay. Then, for greater value, it is purely academic to describe what happened of F0. Again, I have the same kind of behavior. I have here a fixed point, classical fixed point that can appear. Okay, I have still false singularities, but if again, we could make analysis of what happened around singularities. So you have here a false singularity. We should have to zoom to understand a little bit more, but we have this fixed point that corresponds to periodic solution. So we could make a zoom. So you see here you have periodic solution that seems to be stable, and here you have 4 is again a saddle node. But what happens? The following thing happens. In fact, for some initial conditions, well, it's arbitrary, it's academic, you start again from here, so you reach the tau-zero, you have evolution. You have one jump, you have evolution, one jump again, it is seen here, it is N2, here it is N1, so we have a transient with 2 jumps that are governed by the false singularities, but you have here in fact, if you look here, it is not clear. The evolution is like that. You have a jump, you follow the branch, you have a jump, but then you have evolution to the fixed point that is a periodic solution. It is what is seen here. You have, and you see that you have modulation. It takes time to go and to approach the fixed point. By the way, it is normal. Here it seems to be better. N1 is, you see, almost a fixed point. Here you have the effect of higher harmonics. So N1 it's okay. N2, since N2 is associated to purely nonlinear, it is not so obvious, but it corresponds also to a steady solution. So the behavior of the system appears to be on the on this branch of a tau-zero invariant, and in that case you design an S, you have perhaps modulation and 1 or 2 cycles that traps the behavior, but not for a long time. Quickly you will reach a high amplitude oscillation. Okay, so if this is another case, it is even perhaps more obvious in that case. It is similar, I will not discuss. Okay. Now let us consider the second case, n equal 2. So for n equal 2, I take the same Book-Venn model. But I consider now a cubic nonlinearity. So it is quite similar. You have again phi1, phi2 equation by Manevich, okay, completely similar. You have also, it seems to be similar, you have a relation, but algebraic relation associated to the differential equation governing the internal variable, but it's only algebraic equation. Okay, at epsilon 0 order, we could have the invariant, so it is similar, yes, it is similar invariant because also in previous case I have taken the cubic nonlinear terms. So I have the same tau-zero invariant, but here I have this phi3, and at epsilon 0, now you see that phi3 depends on, okay, phi1. You see already delta 3, delta 1, it's the polar form of phi1 and so on. But if I look, okay, no, the phi3 depends on phi1 and the phase, but due to these relations, since you have delta 1 the algebraic relation, we have more complicated relations. So we will obtain again a reduced system. It will be the same than in the case 1, but we will have new definition of capital G function, and we will have new definition of the F1, F2, G1, G2 I introduced in previous case. So simply now we could express N3 in that form, delta 3 in that form. So you see it depends on here delta 2 and 2, and it is the only thing. Here you have delta 3 versus delta 2. N2 and N3, but okay, it's only function of delta 2 and 2. And after some manipulation, we have function H1 and H2, depending on N3, on N3, N1, delta 1, delta 3. And what happened? In fact, now you have the reduced, the two-dimensional differential system, but the fixed point corresponding to periodic solution, and this fixed point will appear in the delta 2 and 2 surface, in fact corresponds to the definitions of N3 and delta 3 versus N2 delta 2, and we have to solve H1 and H2 equals 0, but H1 and H2, you see, depends on, okay, N3 delta 3, N1 delta 1, so it means we have to write, and here it will not be done, it has not been done analytically. In fact, it is not so simple to reduce the analytically H1 to only a function of delta 2 and 2. We have simply to solve these equations. So here it is fixed point, here it is false singularities. For false singularities you find again N2 values, but we have to solve in fact H1 depending on delta 2, delta 3, and H2 also that are equal to 0. And finally, it means it is quite similar, except it is not so obvious. It means the interesting thing is here you have N2 delta 2, and here you have some points. So you see you have stars and circle probably. The stars correspond to fixed points. You have here fixed point, okay, and this corresponds to false singularities. But we cannot obtain directly. We have to solve numerically the H1, H2 equations that are 0, and okay, it has to be done then numerically. Analytically, we cannot reduce directly the behavior on the N2 delta 2 space. We have N2 delta 2 and a manifold that is associated to the equation of internal variable. But then it is quite similar. It means you have, for small value of F0, you have, starting from initial condition, you reach the invariant. Then perhaps you have here modulation with quasi-periodic. Okay, you see, you have a strongly modulating response. The energy after a transient is trapped. Okay. If you take a larger value, you have the same kind of study, but here you see that you have no intersection, so it means you have fixed points but no false singularities. And if you look at what happened in that case, okay, it is quite similar. Okay, it is quite similar, but you start from initial condition, you reach the tau zero invariant, but in fact you see that you have even no evolution here. In fact, you have a kind of evolution, and you have a reversible, and you tend to a fixed point, one of the fixed points, and it could be seen here. You have N1 is in black, so you have evolution and it tends to a periodic solution. N2, it is similar, but you have modulation with higher amplitude, it is not so obvious. And if you go to Y1 and Y2, in that case you have oscillations. Okay, they are perhaps limited, but they have high amplitudes because you do not have efficiency of the nest trapping energy in that area. Okay, so it is what I explained in several parts. It is, you could design a nest to control what happens under initial impulse, then under transient, it means a short seism, let us say, by the design of the nest based on initial impulse. And if you intend to design a nest to control what happens for a solicitation that is periodic or that is considered to be long versus the phenomenon, you can use what I explained here. And you see here that it is based on study of classical critical points of reduced dynamical systems. And here the reduced dynamical systems is associated with the amplitude and phase of the nest. Okay, so I think I told everything here, and by the way, something is stupid but interesting. If you want to apply nest to a car, because for the building I show you horizontal oscillations, but to a car it is vertical. It is very unpleasant. It is unpleasant because you have effect of gravity, and okay, if you take a cubic. So you do the same system of snap-through truss, obviously you will have an equilibrium that will change and the nonlinear part will be destroyed. So you have to take into account the effect of gravity. So it has been done in a paper. So you introduce in the equation the gravity to take into account this fact. And again for y1 being the displacement of the main system, the main mass, y2 the displacement of the nest. Okay, it is possible to do the same same Fourier expansion and same introduction of complex variable, except we take into account the constant term. So it has been done in this paper on nonlinear dynamics, and we show that it can work. And so it is interesting because we could also look and design piecewise nest to be efficient in that case. Okay, so this is the conclusion. Okay, I explain you how to use multiple scales, but to analyze not only steady state behavior, but also transient behavior, being a little bit clever with epsilon that is given finite parameters, and how the study of dynamics at epsilon 0, mainly an epsilon 1 scale, can lead to the efficient design of a nest, and everything is based on analysis of fixed point and bifurcation points, and okay, it could be useful to make design of nest for passive control. So thank you very much. Okay. By the way, I said that I will give you, if you are interested, a few references. So, okay, it is not, I give general references, for example, about nonlinear modes and reduced order models. I do not give all the references I have, only a few, but it is already a lot. I could make comments, you know. Here, Rosenberg, it is one of the first papers introducing normal modes. Here you have two papers around the same years based on normal form to build nonlinear normal modes, but with weak nonlinearities. And the goal were here to build modal superposition. Obviously it is false, but approximate the modal superposition. Then you have a lot of books or papers dealing with nonlinear modes. Okay, and applied to okay, you have applied to some spatial mechanical systems, vibrations of shells, of plates, of beams, and so on. Okay, you have also a lot of papers and books about energy transfer. So I think I gave, it will be on the site. And Okay, we also have papers dealing with energy transfer, with some of them with Oleg, with Leonid Malevich, and with. By the way, we also studied what happens when you introduce several nonlinear energy sinks in series or in parallel, because you have perhaps a natural ID that could be useful. If you take one lightness. Okay, you design, it could be efficient for one mode. But it is also sometimes better to say I take the same mass, but I divide in two, and I design two lighterness. Okay? And okay, it is, we show how to design in such a case. Okay. So here we have some results. Dealing also with robust behavior. When you make experiments, you see it is quite robust. Even if you make a bad experiment with a bad choice of rough choice of cubic terms, it works. So it is very pleasant. We started a rough experiment a long time ago, and we go on working on the NES because it works, even if it was a very basic and rough experiment. Okay, what is interesting still? Yes, here we also deal with non-smooth, and recently on varying mass. And I have some new results I have not put there. Okay. So, thank you very much.
Question. In studying the elastic stability of the airfoil by following the paper by Lamarque that maybe is quite similar to yours, we found a strange effect that even the position of the linear energy sinks is important. If you put on one side or the other side with respect to the center of mass, the result can be detrimental or beneficial in controlling the cycle amplitude. Have you encountered some other cases like this in which the position is strategic?
Yes, you have a very stupid thing, but when you want to use an S, for example, in a car, the problem is what I explained. It is the threshold of energy. So in fact, when you have energy carried by external forcing, whatever the origin, if you want to control a mode, you have to be sure that this energy is spread with a level high enough so that the NES will work. So it is not so obvious. Because when your energy is arriving, according to how it is arriving, you could have a lot of energy, but on the mode, what I said is obvious, but in practice it is not so easy. Even if you have a very good model.
Since we have experimented that simply changing the eccentricity of the NES with respect to the center of mass, you change the sign in the equation,
sure.
And this change of sign could be beneficial or detrimental.
I agree.
So we cannot generalize, but I can see you are not surprised at the result.
No.
So we should be careful in placing the control device. Yes.
Question. I've seen that you sum and subtract the linear stiffness to the NES in order to apply I wonder if after that it is still necessary to apply one explication, or you can directly apply multiple scales.
There is not only one method to go to the, I agree, I know. It is possible to use directly multiple scales, yes. But it is very convenient, It is very convenient because, in fact, at once, when you make such calculations, you see at once the relation between amplitude of N1 and you can read the behavior but it's not a scientific reason. It's a simply technical reason. We did like that.